Thank you, Hongyang, and hey everyone. I'm looking forward to this. I hope it's the start of a great conversation this week. But today, I've got a number of things to talk through. Excitingly, today we've got some new research that we're sharing from Wayve that I hope to give many of you a sneak preview of, as well as a data set. And this is actually a photo from that data set. We often talk about building embodied AI. This is one of the driving scenes one of our autonomous vehicles went through in central London. And I think it really epitomizes the true challenge of this problem. If you look at the multi-agent complexity, the dynamic modeling scene, all the different both rules and culture that you have to be able to truly understand to be able to operate through a scene like this. And I want to start out by zooming out before zooming in. So today's talk, I'm going to talk through three interesting topics when it comes to embodied AI. But before we do that, I'd like to just zoom out and share a perspective about what it means to build embodied AI. Now, of course, across science fiction, we've seen this represented by many different characters, from Marvin the Martian to C-3PO. I'm not sure what your favorite one is. But for me, embodied AI, I think, will be the prevailing way that we interact with intelligent systems in the future. We live in the physical world, and this is, in many ways, the next evolution of tooling. From the wheel to calculators to computers, intelligent machines are going to allow us to free up more of our time for us to be able to trust and delegate tasks to these systems and ultimately improve the safety and sustainability of the world we live in. That's the vision. That's the opportunity with embodied AI. Now, we can ask the question what it will take to build such a system. But I also think it's interesting to reflect on how AI has developed over the last couple of decades. The interesting thing I've observed is that different topics have motivated different breakthroughs. When I was doing my PhD, I think it was fair to say that computer vision problems were really at the forefront with breakthroughs from batch normalization to residual connections. Like, everything was coming out of ImageNet and the recognition challenge. Although it's fair to say more recently, I think language has taken that crown, and we've seen language unlock new levels of scale, of interesting levels of feedback. And it's, of course, languages are more compressed with a higher signal-to-noise ratio information content than images. But I'm a big believer in problem-driven research. And what I want to argue is that I think the forefront of AI and where the next breakthroughs are going to come from is from embodied AI. Why is that? Well, embodied AI unlocks that next level of data. Of course, video data is orders of magnitude more, petabytes or exabytes compared to text data. It's an open problem, open domain problem. We can't control the scenarios we drive in, the weather we experience. And so it really motivates a level of reasoning and capabilities that go beyond a constrained sandbox, but something that we can truly trust to exist in the open world. And safety is not a nice to have, it's a fundamental property we need to succeed. And so safety is paramount to solve. We need to solve the AI safety problem to make this a reality. And so how this motivates us from this problem-driven research, I think this will provide the environment for some of the most exciting breakthroughs in AI to come. So watch this space. I think this evolution will continue to grow. And of course, we're going to talk a bit today about multimodality, how it combines models across these spaces, but ultimately the problem, the data set, and the simulation, the measurement signal, is what has been driving AI breakthroughs over the last few decades. And I think robotics and autonomous driving will be the next frontier. Just to briefly introduce Wayve, a lot of people ask me, are we truly building an end-to-end neural net? And the answer is yes, we are. We have our stack that today runs on vehicles, different types of vehicles around the world. It's truly one end-to-end neural network. Sensor input comes in and a motion plan comes out. It's fully optimized through data and offers many advantages over the classical stack of robotics that we've seen in the past. But I think this is starting to be well understood. The interesting promises that an end-to-end learning system provides the world is that, well, firstly, maybe this is underappreciated, but it is computationally homogeneous. What this means is that many different neural network blocks can be put together, and this makes it easy to port to different software stacks. It's not a bunch of multi-threaded microservices that need to have complex communications between them, but it is a homogeneous forward pass of a neural network. This makes it really accessible. It generalizes through data. This makes it scalable because we can expand to different geographies, vehicles, or sensors and have a representation that understands these. It's economic because it can avoid the use of an HD map because we build the intelligence on board the vehicle that lets it understand the world for itself and make its own decisions. And of course, when it comes to safety and performance, we've seen this story play out in many other spaces. And with robotics, the same will be true, that a learning-based system will be able to outperform anything that we can hand engineer. So with that brief introduction, I want to spend the bulk of the talk deep diving 3 topics that are really exciting me and our team at Wayve right now: simulation, models are enabling the future of autonomous driving, and with scale, how we bring this together to build a data. Sound good? All right, so let's start off with simulation. So I want to talk about end-to-end simulation for end-to-end autonomous driving. I hope I don't need to provide a motivation for simulation because it's so clearly important for autonomous driving, for efficiently iterating, understanding performance, or covering the long tail of edge cases. It is a really clear tool. It's interesting how it's a bit of an arms race. You know, if you solve simulation, I believe you solve autonomous driving, or vice versa. And so there's an arms race between these systems to be able to co-develop the driving policy and a simulator. But the interesting thing we are seeing is that the same arguments that are true in driving policies are also becoming true in simulation. An end-to-end data-driven stack is the way to address this. So let's start off with by examining what is out there today for autonomous driving simulation. There are many example systems today, some fantastic systems. I've called out a handful, but there are so many more, from our own Ghost Gym to Waymo Simulator, the open source system Kala, or Wabi World, or et cetera, many others. Let's first consider the desired outcomes that we want from simulation. So with simulation, I think the first thing we really want to see is that it closes the domain gap, but importantly, not just for perception, but also behavior. Closing the domain gap and measurably closing the domain gap allows us to trust such a system. Secondly, we need to be able to simulate dynamic and deformable and complex scenes, because this is where the edge cases lie. It's not just a rigid vehicle, but it's when the car door opens. It's when people step out onto the road. These kind of things is what we need to be able to handle. It needs to simulate the full environment. It's not just about isolating a perception or a mapping stack, but we need to be able to simulate the full world interaction of our embodied platform. Of course, we need to be data-driven and scale. We've learned this many times over. And finally, we need to be able to control it and be able to take adversarial steps to be able to find edge cases and these kind of things. I think these are the main desired outcomes when it comes to simulation. Now, I'm really excited because today, I think we're going to see a first glimpse of a system that can address all 5 of them. So let's see if we live up to the promise. Let's explore this more deeply. So first, some first background is in, of course, novel view synthesis or neural reconstruction. A first building block of such a system is that it's well known today that we can take camera sequences and produce really compelling reconstruction. You can see this play out here in the bottom right. So that's the first building block. Now, if we take such a system, the question is we need to be able to fully simulate the entire environment. And so taking such a reconstruction, it's not just enough to be able to, fly a camera through a reconstruction. We need to be able to simulate the robot, the vehicle dynamics, the full interaction of how this interacts from a and it's not just the dynamics, but also the latency in the system. There's latency in inference. There's latency in sensor message passing and all of these kind of things. And so Ghost Gym is what we call internally at Wayve the simulator that gives us this entire package, the full latency and environmental simulation coupled with unparalleled realism of the world we interact with. So that's the foundation. This is something we talked a lot about last year, and I want to show how we can build on this to unlock all of those objectives assume yes. So let's jump back to PRISM. So you can see the dynamic agents, right? This is complexity that's super exciting to us. Let me show you another one. So here we are providing a sinusoid input just to really show the novel view generation. And look at the lady with the umbrella. You know, this is incredibly complex. You can see her hand wave, you can see legs move. The level of reconstruction here is incredible. This is from one sequence of us just driving through the scene. We've now been able to entirely resimulate this environment to the point where we can drive back through it. If you look at the reflections, even the traffic light change, if you watch again, look at it go from red to green. It's another example of, simulation is not just putting rigid bodies through the world, but you've got to be able to deal with changing brake lights, traffic lights, other deformable and dynamic objects, making sure that there's a degree of realism when it comes to shadows and everything else. And that's what we're really excited to see with PRISM. Here's another one where we drive through quite a complex and cluttered construction scene. Here you can see we can pause time and look around the world, and you can see the quality of the reconstruction that can come out. Here's another one where we pause in space and we control the time dimension. And you can see here, this is really providing a robust path for full closed loop simulation. You can see on the on all of these examples, we're able the traffic light moving in the top left to pedestrians and vehicles in a rainy scene in the bottom right. Here we can really provide a closed loop driving simulation experience with the full complexity of, for example, urban scenes that we drive in. Even look at the lighting conditions. So on the right, you can see that lens flare that's coming from the reflection on the building on the right, or on the left, the reflections that we see in water. These are things that would be extremely hard to get through a rendering engine, and we can do them in real time through PRISM. So that's a bit of background about the rendering engine within PRISM, and of course that's one important part of it. I've got to stress that the full dynamic interaction, the full latency modeling and robot simulation is what really makes this powerful. So not just PRISM, the second thing we're excited to release today is Wayve Scenes 101. This is a new data set that we're excited to release to the community for a number of reasons. Firstly, we found when developing PRISM, there wasn't a very strong way to benchmark these systems. A lot of the data out there was in very scenes with low complexity that lacked dynamic things from traffic lights to pedestrians to that photo I showed you at the very start. They lacked geographic diversity. And interestingly, they lacked a multi-camera view where there were cameras at significant baselines. And so we've been able to construct a data set here and even propose a benchmark where we have a held out camera at a novel viewpoint that's over 1 meter baseline from the other cameras. And so this is Wayve Scenes 101. Now, here's some example videos from it. You can see here, the diversity in visual scenes from night to rain to day. And more interestingly, here's that scene at the top that I was talking about before. Now, I think this is going to set a true benchmark. Eventually people will overfit to the scene, but it's going to take some time because this is a really complex scene to dynamically render. If you look at how many moving pedestrians there are on the scene, I cannot wait to see progress in this. And we hope that this data set provides a new challenge for complex visual reconstruction. So that's the reconstruction engine and the data set. If you remember, the last thing I was talking about was being able to control the simulation, to be able to take adversarial steps, to be able to try things that perhaps are not present in the original experience. And that's really where we think a simulation can help close the gap and help boost the signal that we need from edge cases to be able to produce a safe and reliable driving experience. So let's talk about that. I want to start by recapping GAIA, a model that we released and talked about at CVPR this time last year. So GAIA is a generative world model that, to briefly talk about the architecture, it allows us to encode vision, language, and action into tokens, to pass them into an autoregressive world model that allows us to, for example, decode and understand, decode and generate sequences of driving. And we can use it to we can condition it on various inputs, but we can use it to build a world model that can really understand scenes like the complexity that we've been looking at. And if you want to learn more about it, you should speak to Anthony, who's in the room, who led a lot of this work. But of course, GAIA is part of a full ecosystem of world modeling. This is a great figure from a survey linked at the bottom on this space. We started working on world modeling. We put a blog out in 2018 that showed how to build a model-based reinforcement learning system to our system MILE here. Or GAIA, or there's many others now, right? This is a really rich and important area. If you have a world model, if you have a system that really understands the dynamics of the scene, it will be a representation that goes a long way to be able to drive robustly. And so just to, again, introduce GAIA, it's a system that can generate sequences that we can control. Now, all of these videos are synthetically generated with the world model from different weathers to different times of day. And it's all generated from scratch with this with the system. Now, how can we utilize this to control the simulations that we're building? Well, interestingly, in GAIA, we can control and inject edge cases. Here, we ask the ego vehicle, we condition it on forcing it to the wrong side of the road. And then you can see how the scenario plays out. You can see some realistic and interesting behavior result. And we can, of course, synthetically create edge cases like this. A sneak preview of what the latest system is able to do. Well, we can now even control dynamic agents within it, and even add on to simulation systems such as the PRISM system I just showed, and add new agents. Now, this is fully generative, so everything from the shadow to the lighting to everything like that is coherent with the entire scene. And here you can see we've artificially placed the vehicle using GAIA in a driving scene. Here's some more examples. We've asked it to place a bus or other vehicles. And this is an interesting one where all of the dynamic agents in this video are rendered through GAIA. And you can see there's a truck in front of us. There's cars on our right in the other lane. Now, the interesting thing is these are 3 camera views. Now, if you look carefully, the car that drives, the sedan that drives on our right, it's coherent between the camera views. It comes through the middle one and passes to the right, and it's the same car. It's generated from a unified representation across the multi-sensor, multi-view stack, and that's really important. So GAIA lets us control and modify the scenarios that we drive in beyond what we've experienced before. I'm going to talk more about Lingo later, but in short, it's a system that can allow us to ground our driving experience in language. But just to pull this forward, you can see here that we've been able to, on the left, introduce a car in front of us and ask Lingo what it says about the scene. Here, it wants to increase speed to match the speed limit. And at the bottom, it wants to slow down to match the vehicle's speed. And on the right, you can see that it again, adjusts to counterfactuals based on us controlling the environment. And the final example is in PRISM. Here you can see we can add and remove dynamic agents from the scene quite effortlessly. So the point being, I hope now that those promises or the requirements of simulation I laid out at the start, from complex dynamic deformable scenes to being controllable to simulating the full environment and embodied system, this is now a system, GhostGym, that can holistically address them all. And we believe provide a data-driven path to be able to scaling up simulation for autonomous driving. Great. Let's move on to the second topic on multimodality. So I want to talk about vision language action models here, grounding driving and language, and some of the work that we've been doing in this space. Now, why would you want to bring in language into embodied systems? Well, language allows you to unlock a new, greater source of training data. Text can be a really high signal-to-noise ratio of information. It's a lower bytes to intelligence form of data. It can provide general purpose reasoning from the wealth of human knowledge. And more interestingly, enable features that might provide a greater degree of trust and safety through enabling language interaction with robotics. There's a number of reasons why it's interesting to us. And if you want to read more, there's an excellent survey here, actually by some of the people in the room, that you might want to read more about language meets driving. So this time last year, we were talking about Lingo 1. Lingo 1 was our first vision language action model that was enabled to do VQA around driving scenes. It could watch driving scenes and interact through language. Essentially, we encoded driving experience and passed this through a language model that we fine-tuned through both image input plus text input. and we were unable to enable a conversation as a result about the driving scene. That was the core architecture. Quite simple conceptually, but a amazing challenge to train and assemble the right data for this. But the result was a system that could comment and explain driving, like you see on the left here, where it's describing that it's slowing down for a jaywalker and navigating through the scene like this. Or on the right, you might not be able to read this, but where it can actually answer questions. And we ask it, what are you seeing? What are you looking at? And it describes, I'm seeing a glass building. There's a risk of a van on the left, and there's a cyclist on my right. And it's able to actually give grounded answers of what's in the scene. Quite exciting results. We could even take it one step further where it could do referential segmentation. This really reduces any tendency of hallucination because it asks it to ground its answers in the visual scene. So you can see here, our system is able to point to what it's looking at, the road in front. You can see it's labeled, or the car in the background. And we can even ask it what do broken road lines mean. You can see it can highlight them on the screen. And so this is referential segmentation. What I want to talk about today is Lingo 2, which goes a step further. It actually brings this model for the very first time, we believe, in the world. It brings a vision language action model in closed loop driving a car. This is super cool because it actually means that this is not just commenting open loop, but it's actually the same representation that's driving the car and understanding the world. And you can read more about it in our blog. But this, so essentially the architecture is it's end-to-end trained, but we pass in vision data and feed in those tokens as well as text and other prompts like navigation into a VLA model that we can then use to drive the car or converse with in conversation. So that's Lingo 2's architecture. Let's look at some of the results. So if you look at this, this is this is actually driving the scene. So this is Lingo 2 driving in closed loop while also describing the scene. And if you look at that, you can see it's talking about, why and what it's doing. I can show you another clip here. This is quite interesting. You can see it's the road's clear. Now it starts to talk about, oh, there's a bus, and it's actually wanting to overtake the bus. It's quite a hard thing to recognize, but it's recognizing the bus is at a stop. Then it's going to come back in the left lane and then slow down for the traffic light. And so this kind of level of reasoning, I mean, this is a true generalization test, right? This is never present in the training data. We're driving in London here, and you can see how the system is grounded in reasoning about the world. Well, here's another example where you can see it's talking about, well, what's it going to say? The zebra crossing is clear, how it's driving through the space in central London. So that's essentially what Lingo allows. Now we can interrogate and learn more about it in Ghost Gym, which I just introduced. You can see here that we can prompt and ask it to follow the route, or we can slow down for the turn. And you can see that we can actually start to control the behavior of the vehicle through language. We can even ask it to stop behind the bus or overtake the bus. And you can see its behavior will actually change conditioned on text prompting. What does this enable? Well, we can start to talk to our car, have a chauffeur experience. We can ask it to drive in a certain way with a certain style. And it can be prompted by this. Of course, it will do what it believes is safe, but there's a large operational envelope of what you can do within what is safe driving. And we can start to control that quite naturally through language. Really make this successful. You don't need a research degree in robotics to understand this car. We can just talk to it in natural language. I think that's super exciting. And really, what we believe is that by using multimodal training, we can provide greater alignment and create general purpose knowledge into our driving model so that it can be safer and a more performant driving experience. Let me, so that's on multimodality. Let me just move on to the third and last section on engineering to product. So we've talked about a simulator and why this is important for self-driving. We talked about multimodality. The thing that I'm really excited about at Wayve is the opportunity we have to now take this work and really deploy it, to build the ChatGPT of embodied AI, to get the system out there at scale that can enable people to be delighted by an embodied AI experience. So what's it going to take? And I say this because often my experience in, when I've spent time in the research community is that often people dismiss engineering. Reviewers, of course, don't value research, don't value engineering as much as they do novel ideas when it comes to accepting papers. But I think engineering is, well, one, scale is super important when it comes to enabling AI, but two, it's often underrated, and it's the key thing that turns a demo into something that's truly robust. And for anyone who's a technologist, I think that's something to get really excited about. And so I hope that this section can talk about some of the problems and opportunities when it comes to building a foundation model for embodied AI. So let me start off with, again, a bit of the motivation of what we want to create here. Well, at Wayve, we want to build a generalizable embodied AI platform, something that can enable not just driving, but domestic robotics, manufacturing robotics, essentially enable us to trust and interact with machines in the physical world. How are we going to do that? Well, we want to learn from the most diverse data across the industry. We want to be agnostic to the specific robot so that we can learn and deploy from various different data sources. We don't need a homogeneous fleet, but we can really learn from diverse vehicles. We want to be truly excellent when it comes to inference efficiency, so we can pack as much intelligence as we can into the compute. And finally, have provably safe and I think the more important word here is predictable behavior. We want to be really reliable with what we can and can't do, so we can set bounds and expectations of what the system can be used for. So that's the motivation. That's the North Star. How are we going about doing this? Well, at Wayve, we're building a foundation model for embodied AI. So this word's thrown around a lot. The definition we use for foundation model is a model that's trained on a diverse set of experience that can be general purpose, used for a number of tasks. And for us, that's tasks across the embodied AI space. Now, there are many examples of this across language and vision. What about language, vision, action? What about embodied systems? Well, there are some unique challenges for embodied AI, right? Data is one. We can't just scrape the web. You've got to have interaction with physical systems. I think this is where self-driving has an advantage, because there are hundreds of millions of vehicles, if not billions, around the world driving today that can collect data, that are collecting data already today. And so this is, there's already a commercial setting for that. Training compute. As with language, we can't just put all the data locally on a compute node. You need to be able to stream petabytes of video to GPUs. And of course, actually embodying it in the world, from safety to the actual integration and interface, these things are hard. Now, there are a number of examples also in embodied foundation models, but nothing that's hit a sort of GPT-4 level of scale yet. And that's what we want to unlock at Wayve. So the first one is with data. Let's talk about the data that we train on. Of course, there's the driving experience we have from our fleet, and we've seen a lot of that today. But there's a whole pyramid of this. And I think the base level of data starts with internet scale videos that give you that general purpose understanding of the world. There's, of course, embodied applications from many different types of robots. There's large-scale driving data that we work with our partners on, from Asda and Ocado, two big fleets in the UK. And of course, the high-quality driving data that we collect ourselves. But together with our partners, Microsoft and NVIDIA, we are training these systems now at a level that I think the world hasn't seen before. And the results are incredible. Here's some example of just really how diverse the data is. And if you learn from this kind of data and can't learn a general purpose sense of reasoning about the world, I don't know what we're doing. I think this is truly, captures the full breadth of physical interactions that we experience. And of course, will provide general purpose knowledge for driving that goes beyond the edge cases that we will have seen in our training set, but the full breadth of the open set world that we need to be able to operate in. So bring this together, this is enabling us to train a foundation model that's trained on many different domains of data, many different sensors, from camera to camera radar, to camera radar LiDAR, to other sources with many different outputs, and will just be the most general purpose embodied AI model that can be deployed for safe driving and other robotics applications. So that's the system that we are building, and it's enabling the kind of results that we're seeing. And there's many videos on our website if you want to check them out. But our ability to drive through areas as complex as central London is possible because of this kind of infrastructure and scale. And so the final point on this topic I wanted to make was about how we actually bring this into automotive. And part of this is about building a system that can be not just behaviorally safe, but also functionally safe, but also being able to provide an experience that can start as driver assistance, can see the system deployed at scale, and before ultimately being evolved into an autonomous driving experience. And we've been able to put together an architecture that retains the benefits of being end-to-end and data-driven, while providing a full safety case that allows us to use data-driven methods to be able to put together a SOTA, first a behavioral safety case that allows us to provably and measurably allow for performance within a certain operating domain, plus enabling all the functions from L0 all the way up to L5, from driver assistance and warnings and active safety to perception, all the way up to autonomous driving in a generalized way, which we call L5 driving. And so this architecture is again a really important part of engineering. And while it's perhaps not as interesting from an academic or algorithmic sense, it's absolutely critical to be able to getting these systems deployed in real life automotive environments. Great. So let me conclude, and then I'll be happy to take a couple of questions on this material. But I hope that today's talk inspired some ideas in Embodied AI. I hope it starts a conversation, and we've got a booth this year in the expo with a number of our teams. So please come and speak to us if you want to learn more. But for me, the main conclusions are, firstly, embodied AI is the next frontier of AI. It's unlocking the next level of scale and complexity of a challenge that will motivate us to truly solve the physical world and the safety problems with AI. Secondly, self-driving is the best path to build this. There is a commercial use case, there's a societal imperative to get this technology out there, and there is data and vehicle platforms available at scale today for this. We can build trust through multimodality and ground our systems in language. We can simulate complex dynamic scenes without needing scene graphs, but we can build an end-to-end simulator for end-to-end driving. And finally, I'm excited that Wayve is now in a position to engineer a product at scale. And that's what we're obsessive about in our team. So if that's something that interests you, please come chat to us. We're hiring around the world, from London to the Silicon Valley to Vancouver are our main AI offices. And look, we're truly excited to have the opportunity to now bring this embodied AI system out there at scale. So thanks very much. Happy to take any questions.
Questions? Yes. Yeah, I have several questions. So you mentioned about GAIA as a world model simulator, and you mentioned several other models like Lingo. Have you used GAIA as a pre-training for learning the policy, your driving policy? Or are you mostly relying on the Lingo 1, Lingo 2 style vision language model to do the end-to-end driving? Is my first question.
Sure.
My second question is, there have been a general trend discussing about how to best approach the end-to-end driving from we have seen using vision language model, or people have been talking about using a machine learning planner at a higher frequency as a system 1, and using vision language model as a system 2 at a lower frequency. This kind of solution. What's your take on this? And does Wayve believe that everything just need vision language model output that? And the third one is sorry, a lot of questions. The third question is you talk about foundation model and vision language. Obviously, it is very compute cost. And how are you going to bring down this cost and convince the OEM to take your solution? Thank you.
Some memory tests as well. So the great questions. The first one, if it wasn't clear, so we're building a single foundation model across all of these tasks. So a model that has language data, it's language grounded, it's got a world model in it, it's bringing together all of these tasks in one system, and that's the system that's driving the car. And so yes, it's got GAIA world model capabilities, it's language grounded. All of these systems together is what enables the performance that we have of driving on the road today. Second, let me take the third question while it's fresh in my mind around cost. So the exciting thing is that there are vehicles around the world today that have surround sensors, camera radar, they have a GPU on board. And as I mentioned, an end-to-end stack is more efficient. It doesn't need the 4 kilowatts of compute that you might see in some robotaxis around the world, because it's a homogeneous end-to-end system that can be very compressed and optimized for inference. And so we're excited that there are millions of vehicles being produced today that have the hardware requirements to run this stack. And so we don't need to convince the automotive industry to change their vehicles. We can deploy this AI on vehicles that have been built today. And that's why one of the reasons why I think autonomous driving is the way to scale embodied AI. If you think about humanoid or manufacturing robots, there's a whole fleet and hardware bring up problem. But for driving, it already exists today. I'm so sorry. The second question was
Using the vision language model versus like using machine
Oh, the
learning?
hierarchy. Yeah. I mean, we of course, we're exploring a number of hierarchical approaches as well as just a single system. I think the jury's out. There's pros and cons to both, and it's an area of active exploration for our team. I'd love to. We should debate it. Yeah, I'd love to debate that topic.
Yeah, please.
Thank you, Kendall. The simulated data, do you use the scale for training, or I noticed that in the data slide it was not part of the data sources.
Oh, it was. Maybe I need to update this slide. If not, there's synthetic data here. So yes, we use our simulator for yeah, of course, for synthetic data, for training, for evaluation, the full suite of things. Yeah, it's a growing part of our data source. I won't share the exact breakdown because it changes week on week, but it's certainly a growing part.
But what's the next? I mean, generating huge amount of simulated data. Do we see some observations as to the performance improvement in some like motion prediction or planning? So I haven't figured out what's the use of this simulated data. That's why it also confused me as well.
Yeah, I think there's many uses, right? Let me talk about one specifically I'm excited about, which is being able to create adversarial examples. Now, if you try to simulate the entire operational design domain of driving, you're going to use half the world's compute. Being able to more efficiently find areas where your policy is uncertain or broken, and being able to take an adversarial step to be able to learn from how the system's behaving. I think that's one of the most exciting opportunities with a simulator, is being able to boost the training signal in the areas where the policy needs it the most, which by definition are edge cases.
Yeah. Okay. That'd be great. All right. Go ahead.
So your second last slide or something is a safety by design. You have secondary computer that the end-to-end driving model that can simply further. So can you talk a little bit about how that segregation makes sense, and does it like really guarantee that
Yeah, I mean, the great thing about this architecture is it's an architecture that scales all the way from L0 to L5. Now, there are many ways you can change it. You can architect this to be on a single computer if you want, with various trade-offs and things like that. But this is one instantiation of it. And so, the important thing here is that we're able to make arguments around redundancy. We're able to make arguments about a Swiss cheese model of safety, failure modes that are anti-correlated, things like this, and we're able to show them empirically with data. So that's one of the exciting things about this architecture. But as I say, it's designed to be something that, well, it is capable of being deployed in production vehicles today, and it can address L0 to L5. It's really a function of data. The more data and that you can train the system on, and then of course validate that it can acceptably drive in a given area, will allow you to advance up those levels of autonomy. The secondary computer could be a ring-fenced area on an ECU. It could be literally a secondary computer. It's I guess a redundant piece of compute that doesn't that has some redundant failure mode.
looks like a high level of
I wouldn't advocate for object detection. I mean, really, we're looking to use self-supervised end-to-end learn systems for safety. I mean, that could be one way of solving it. There's many signals that you want to get out, but ultimately we want to be having data-driven systems that provide antagonistic signals via to build a robust I guess trajectory decision as an output.
Yes.
Does multimodality result in just better action prediction, or it's just for explaining everything?
Both. We've seen evidence that multimodality, well, one, it improves driving performance. Two, it improves behaviors. In particular, we saw some improvement in multi-agent interactions around busy intersections. And then, of course, it enables new features like you being able to prompt and a certain behavior, or actually debugging or asking questions around why the vehicle is making a certain decision.
Yeah, please.
Could you share a little bit more about this 4D reconstruction PRISM 1? And I would like to know how you guarantee consistency across different cameras. We have different cameras facing different directions, right? And for them, how that is very important, how you can the 3D poses of the dynamic objects can maintain those kind of consistencies. Also, 3D poses probably not important at all in this and eventually. And yeah.
Yeah, it's a super question. Let me jump back to one of these videos. So one I want to show is, I'm most excited about this one here, right? Because here we've got cameras that are, quite significantly perturbed in space and time. And you can see the consistency and the fine features like the color of the traffic light, or the poles, or of course the pedestrian. That's, I think, the highlight of the scene. Yeah, so this was a lot of the really challenging work for us to get this to working. Get this result was to be able to have a unified representation from a surround camera rig, and more importantly was to be able to train a 4-dimensional neural reconstruction method that can respect the time domain. We're not yet ready to release any technical details of how we do it, but I can show the results and talk about the pros and cons of it at this stage. And but you've highlighted the key challenge in getting this to work.
You have to reach in one different camera parameters, visual camera and display.
You can resample and you can re-render an image with a different camera. You can just set a pose and a camera parameters and resample an image without retraining the model. Yeah, that's important because we drive vehicles that are vans and cars. They have very different camera poses, and so we can easily transfer between the two using these kind of models.
Yeah, the last one.
I think so. Of the data moving part, there are many cases for the all the simulator is learning from the data. I was wondering whether how is this integrated for the or how you look it down.
So the question is, how do we simulate corner cases? Yeah. Well, the first one is we can create corner cases. So I was showing some work how we can insert new agents, or we can change behavior or features in the scene to be able to create an adversarial example. That's that's one way. Or the other way is you want to be able to find edge cases, and there, one of the other things I'm excited about is how good these foundation models are, and using their embedding to semantically search across data and actually find the edge cases. We do this regularly at Wayve in an unsupervised way, where we have petabytes of driving video that we can search through the embedding representation of our foundation model and use that to find, I don't know, if you want to find like going through a roundabout in the rain with a cyclist on your right, we can find many examples like that. Or if you want to find a pre-crash scenario or something like this. And so, finding those examples where they are is one way, or the other way is finding adjacent examples and augmenting them by adding or changing agent behavior to be able to create that scenario. Those are the methods that we employ. Super.
I think we might have the last one. Yeah.
So there's a safety part in the autonomous system that beside the engine itself. To explain a bit more about this part, why the system needed and how to do it.
Yeah, that's I'm probably not going to give a super satisfying answer here, because we've spent 8 years building end-to-end learning systems for driving. and 8 years studying how to make them safe. This is one of the hardest problems, is how do you build an architecture that retains end-to-end learning, being data-driven, self-supervised, all of the benefits of AV 2.0, while also being safe in a way that complies with automotive expectations. This architecture achieves exactly that. And it's, it's a key part of what is required to be able to turn this into a product. It's something that is fairly, fairly core IP to us. And so it's not something that we can talk about. I know that's a frustrating answer, but I do want to plug that in general, we are and have been and continue to be quite an open company when it comes to talking about research. I've been speaking at CVPR for the last 7 years straight, talking about the work that we're doing, sharing new results. We regularly publish papers. We're writing up work like this at the moment. GAIA and Lingo have both been published in full technical reports where you can read about them. And so we do talk a lot about our work. When it comes to building a product, we're super excited to have that opportunity, to have the compute, the capital, the data to now go and build a foundation model that can be deployed in automotive and crucially make it safe. And so that's a key thing for us as a business right now. So we're looking to balance those things. We are focused and heads down on building that out. But when it comes to scientific discovery, well, what we have today here is exciting and on the cutting edge. There's still a gap from here to really a general purpose embodied AI system. And so we certainly believe that continued publishing, discussions, debates, and communities like this is something that is really necessary and wanted. And so that's how we think about things at Wayve, if that helps.
How do you compare your work or from the Wayve, right? That lots of interesting work. We really do appreciate, and with other company or research institutes like Tesla or Vivo or NVIDIA, right? There are lots of other works from them. It's just for curiosity.
Yeah, well, there's two answers to that. The first one is that we've had the privilege of doing some things for the first time. And when you do something for the first time, there is no, there is no benchmark. I actually remember publishing a paper back in 2015 on localization with end-to-end learning called PoseNet. And there was nothing to benchmark. So I created a data set around it. Now, the benefit of that is the work was, the performance was so lackluster that everyone cited it as a result because it was an easy benchmark to beat. But you've got to start somewhere. So we have started somewhere in many of these areas, and it's taken us 8 years to build up to the level of performance now where, for those of you that have come for a drive in one of our cars, it's truly exciting and robust and generalizable. You can drive anywhere within the domain it's trained on, and it's it can drive through the most complex scenes, like the one that I opened with at the very start here. For when you are working on something that does have others working on it, and you listed some examples, Hongyang, of course there are KPIs you can benchmark. Distance per disengagement is a key one. Scenario success rate, going through, for example, like a unprotected right turn with medium density pedestrians around you in the rain could be an example of a scenario. You can look at the success rate of being able to go through that. These are the kind of things that we measure internally. And of course, there are somewhat well-known metrics around the industry of what great looks like in those areas. And